Think about the night sky for a second. We look up and see a universe that looks fairly static, but the truth is much more dynamic and, honestly, a bit unsettling. In 1929, an astronomer named Edwin Hubble changed everything we thought we knew about our place in the cosmos. He discovered that the universe isn't just sitting there, it is expanding. But he found something even weirder. The farther away a galaxy is from us, the faster it appears to be moving away. This isn't just a small difference, it is a fundamental law of the universe. If a galaxy is twice as far away as another, it recedes from us at twice the speed. This discovery, which we now call Hubble's law, provides the bedrock for our modern understanding of the Big Bang and the evolution of the entire cosmos. The first thing we have to do is address what expansion actually means, because our intuition often gets it wrong. When you hear the word expansion, your brain probably pictures an explosion, like a bomb going off in an empty room, sending debris flying outward into pre-existing space. But that is not what is happening with the universe. In an explosion, matter moves through space. In the expansion of the universe, galaxies are not moving through space in the traditional sense. Instead, the fabric of space itself is stretching. Imagine a grid. If you take that grid and stretch it out, every point on the grid moves away from every other point. The galaxies are like dots on that grid. They are being carried along by the stretching of the space between them. This distinction is vital because it explains why physics doesn't break when we see galaxies receding at mind-boggling speeds. We measure this recession through a phenomenon called cosmological redshift. As light travels from a distant galaxy towards Earth, it has to move through this expanding space. As the space stretches, the wavelength of the light traveling through it also stretches. For light, a longer wavelength means it shifts toward the red end of the spectrum. The farther the light has to travel, the more space it has to cross, and the more it gets stretched. By measuring how reddened the light from a distant galaxy is, astronomers can determine exactly how fast that galaxy is receding, and consequently how far away it is. This relationship is so precise that we can use it as a cosmic measuring stick. But the question remains, why does distance dictate speed? Why isn't the expansion just one uniform speed for everything? To understand that, we have to look at how the cumulative nature of space works. When you have more space between 2 points, you have more fabric that can stretch, and that simple geometric fact creates the terrifying speeds we observe in the deep universe. To really grasp why distance determines recession speed, we need to use one of the most famous analogies in science, the balloon. Imagine a balloon that isn't inflated yet. You take a marker and draw several dots on the surface of that balloon, each representing a galaxy. You place them at equal intervals, let's say 1 inch apart. Now start blowing into the balloon. As the rubber stretches, the distance between every single dot increases. If you focus on one specific dot as your home galaxy and look at the dot right next to it, it might move away by 1 inch in a few seconds. But look at the dot that was originally 3 inches away. Because there were 3 segments of rubber stretching between you and that distant dot, each segment adds its own inch of stretch. In the same amount of time, that distant dot has moved away by 3 inches. It appears to be moving 3 times faster than the dot right next to you. This is the key to understanding the Hubble relation. The expansion of the universe is a local phenomenon happening everywhere at once. Every megaparsec of space, which is about 3.26 million light-years, is stretching by a certain amount every second. Currently, that rate is estimated to be around 65 to 70 kilometers per second for every megaparsec of distance. If a galaxy is 1 megaparsec away, it recedes at 65 kilometers per second. If a galaxy is 10 megaparsecs away, there are 10 individual units of space, all stretching simultaneously between us and that galaxy. Each unit contributes its 65 kilometers per second to the total. Therefore, the distant galaxy appears to be rushing away at 650 kilometers per second. It isn't that the distant galaxy is trying harder to move, it is simply that there is more space between us and them to do the stretching. This reveals a profound truth about the structure of the universe. The expansion is not a force pushing galaxies through a void. There is no cosmic engine at the center of the universe shoving things away. In fact, one of the most important observations in cosmology is that there is no center to the expansion at all. If you were to teleport to a galaxy billions of light years away, you would see the exact same thing we see from Earth. Every other galaxy would appear to be moving away from you, and the ones farthest from your new home would be moving the fastest. This uniformity is what we call the cosmological principle, the idea that the universe is both homogeneous and isotropic on a large scale. It looks the same in every direction and from every location. The expansion is a property of space itself, an inherent stretching that happens to the vacuum. This means that we aren't at a special spot in the universe just because everything seems to be running away from us. We are just one of many observers watching the fabric of reality grow. A common question that follows this is, if space is stretching everywhere, why aren't we stretching? Why isn't the solar system or the Earth getting bigger? This is where the competition between forces comes in. Gravity is the great organizer. While space is trying to stretch everything apart, gravity is working hard to pull things together. On small scales like the scale of a galaxy or a solar system, gravity is incredibly strong compared to the relatively weak stretching of space. The gravitational pull of the Sun is more than enough to keep the Earth in a stable orbit, completely overcoming the expansion. Even our local group of galaxies, which includes the Milky Way and Andromeda, is held together by gravity. In fact, Andromeda is actually moving towards us at about 200 kilometers per second because the gravitational attraction between our two massive galaxies is stronger than the expansion of the space between us. It is only when you get to the vast, empty reaches of intergalactic space, where gravity becomes incredibly weak because of the extreme distances, that expansion finally wins the tug of war. This is why we only see the farther galaxies move faster rule apply to objects that aren't gravitationally bound to us. This reveals a lot about the structure of the universe. It tells us that the universe is organized into islands of matter. Within these islands, like galaxy clusters, gravity rules and the structure remains stable. But the space between these islands is where the real action is. That space is stretching relentlessly, pushing the islands further and further apart. This brings us to the Hubble relation and what it really tells us. The number we use to describe this expansion, the Hubble constant, is more than just a speed limit. It is actually a measure of the age and the expansion history of the universe. If you know how fast things are moving away and how far they are, you can essentially run the movie backward. If everything is moving apart now, it must have been closer together in the past. If you trace those paths all the way back to a single point where everything was compressed into an intensely hot, dense state, you arrive at the Big Bang. Based on our current measurements of the expansion rate, we can calculate that this beginning happened approximately 13.8 billion years ago. The fact that farther galaxies move faster isn't just a quirky observation, it is the evidence that allows us to calculate the very birthday of existence. It shows us that we live in a universe with a finite past, where light and time are interwoven into the stretching fabric of space. One of the most mind-bending aspects of this expansion is that it can actually exceed the speed of light. Now, if you've studied any basic physics, you know that Einstein's theory of special relativity says that nothing can travel faster than the speed of light, which is about 300,000 kilometers per second. So, how can we have galaxies that appear to be receding from us at speeds greater than that absolute limit? The answer lies in the distinction we made earlier, the difference between motion through space and the expansion of space. Einstein's speed limit applies to objects moving within the fabric of space. If you try to push a proton or a spaceship through space, you will hit that light speed wall. But there is no law in physics that restricts how fast the fabric of space itself can stretch. Because the expansion speed is proportional to distance, if you go far enough out, you will eventually hit a distance where the cumulative stretching of space adds up to more than 300,000 kilometers per second. Galaxies at that distance and beyond are receding from us faster than light. This doesn't mean they are breaking the laws of physics. It just means that so much new space is being created between us and them every second that light from those galaxies can never bridge the gap to reach us. This creates what we call a cosmological horizon. There is a limit to how much of the universe we can ever see, because beyond a certain point, the space is expanding so fast that light is essentially walking up a down escalator that is moving faster than the person walking. The light is trying to reach us, but the distance is growing faster than the light can travel. This reveals something terrifying about the future of the universe. Because of this faster-than-light expansion, the observable universe is actually shrinking in terms of the number of galaxies we can see. As space continues to stretch, more and more galaxies are being pushed beyond our cosmic horizon. Eventually, they will move so far away and be receding so fast that their light will fade out and disappear forever from our perspective. This process is being accelerated by a mysterious force called dark energy. We used to think that gravity would eventually slow down the expansion of the universe, but in the late 1990s, observations of distant supernovae revealed that the expansion is actually speeding up. Dark energy acts like a repulsive force inherent to space itself, ensuring that the farther things get, the faster they will continue to accelerate away. We are living in a unique window of time where we can still see other galaxies. Trillions of years from now, the Milky Way will be an isolated island in an infinite dark void, with every other galaxy pushed so far away that their existence will be undetectable. When we look at the Hubble relation, we are looking at the pulse of the universe. The discovery that farther galaxies move away faster was the first real clue that the universe has a history. It isn't an eternal, unchanging void. It also reveals the overall geometry of the cosmos. If you think about the balloon analogy again, the surface of the balloon is a curved space. But when we measure the expansion and the light from the early universe, we find something truly bizarre. The universe appears to be flat. In cosmology, flat doesn't mean a two-dimensional sheet. It means that the geometry of space follows the rules we learned in school. Parallel lines stay parallel, and triangles have 180 degrees. How does a stretching universe stay flat? This is one of the deepest mysteries in physics. It requires a perfect balance between the energy of expansion and the pull of gravity. If there was even a tiny bit more matter, gravity would have eventually won, causing the universe to curve inward and eventually collapse in a big crunch. If there was too little matter, it would have curved outward like a saddle and expanded so fast that stars could never have formed. The fact that we see a universe that is expanding but still maintains this near-perfect flat geometry suggests that something very specific happened at the very beginning of the Big Bang, a moment of hyper-rapid expansion called inflation. Inflation was like a cosmic iron that smoothed out all the wrinkles and curves in the early universe, stretching it so much that any local curvature became effectively zero within our horizon. This is why billions of years later we see the expansion behaving so uniformly. The farther galaxies are moving away faster because they are part of a massive, synchronized stretching that was set in motion during that first fraction of a second. This reveals that the universe is a highly structured, finely tuned system. The recession of galaxies isn't random, it is a mathematical consequence of a geometry that was established before the first star was even born. Every galaxy we observe is following a path that was determined by the density and energy of the early universe. By studying why farther things move faster, we are essentially reading the blueprint of creation. What does all this mean for the future? If the expansion continues to accelerate, we are heading toward a scenario called the Big Freeze, or the heat death of the universe. In this future, the farther galaxies move faster rule eventually reaches its logical and lonely conclusion. As dark energy continues to push space apart, galaxies that are currently visible in our night sky will continue to redshift. Their light will be stretched into longer and longer wavelengths, moving from visible light to infrared, then to microwaves, and finally to long-wavelength radio waves until they become so faint that even our most powerful telescopes won't be able to detect them. Eventually, the local group of galaxies, the Milky Way, Andromeda, and their small satellite neighbours will merge into one giant elliptical galaxy. But beyond that single, massive island of stars, the rest of the universe will be gone. The expansion will have pushed everything else beyond the horizon. Any future civilization born in that distant era would look up at the sky and see nothing but the stars of their own galaxy. They wouldn't know that other galaxies ever existed. They wouldn't be able to see the cosmic microwave background or measure the redshift of distant objects. To them, the universe would appear static, eternal, and empty. They would be trapped in a bubble of space, isolated by the very laws of physics that we are using today to understand the cosmos. This is why our current era of astronomy is so precious. We live in a time when the universe is old enough to have formed complex structures like planets and humans, but young enough that the evidence of its beginning is still visible. We can see the farther galaxies move faster, and deduce from that the expansion of space, the Big Bang, and the existence of dark energy. We are witnessing the cosmic fireworks before the lights go out. The structure of the universe, this stretching fabric that carries galaxies away, is a temporary bridge between a hot, dense beginning and a cold, dark end. The fact that distance determines speed is a signature of our universe's growth, a reminder that space isn't just a place where things exist, it is a living, changing part of the story. So let's recap the mystery. We've seen that the universe isn't just a static box, it is a stretching medium. Galaxies aren't flying through a void, they are being carried away as more space is created between them. The farther away they are, the more space there is to do the stretching, which is why their speed increases with distance. We've seen that this expansion is uniform, identical from every perspective, and that it doesn't represent a force shoving galaxies, but rather a geometric property of space-time itself. We've also tackled the big hurdle, the speed of light. We know now that galaxies can recede from us faster than light without breaking any laws, because it is the road that is getting longer, not the car that is driving faster than the speed limit. And we've seen that this whole process is leading us toward a future of absolute isolation, powered by the mysterious and relentless influence of dark energy. This reveals a universe that is vast, beautiful, and deeply indifferent to our presence. The stretching doesn't care if we can see the other galaxies or not. It just continues to expand according to the energy density of the vacuum. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. The fact that we can even understand this, that we can measure the reddening of light from a source billions of light years away and use it to calculate the age of the universe, is a testament to human ingenuity. We have taken the weird observation that farther things run away faster and turned it into a map of our entire history. But as we've seen, this expansion behavior is tied to a very specific geometric structure. If the universe were any other shape, the expansion wouldn't look the way it does. The flatness of our universe is the reason why the Hubble relation is so consistent and why the Big Bang model works so well. But why is the universe flat in the first place? Why did it end up with such a perfect geometry instead of being a warped, curved mess? If you want to understand the strange logic behind the shape of space and why the entire universe is so perfectly level, click here to Why the Universe is Flat video.